Okay, welcome everyone to a brief introduction to deep learning for natural language processing, um, which I will present today. The introduction that I will give is very high level. It's also a rather gentle and like user friendly, I hope so, introduction to deep learning. Rather than giving a lot of mathematical details, I will only give a very high level overview of what deep learning for natural language processing looks like at the moment. And when we talk about deep learning, we keep in mind that deep learning is one of the most powerful and one of the most popular and ubiquitously used approaches in machine learning at the moment, because it has really pushed the state of the art in artificial intelligence in the last 10 years or so. So the introduction that I give today is based on my deep learning course at TU Darmstadt, for which you can find the Moodle link here. So what is deep learning? Deep learning is firstly a subfield of machine learning. So it deals with computers and algorithms that are trained using data and that become better over time using those training data instances. And the particular thing about about deep learning, and we note here firstly that deep learning actually has two names. The original name for deep learning was like neural network learning or neural network architectures, which was basically the name, I think, until the mid 2000s, when some people changed the name to deep learning because apparently it would sound more fancy and would sound more deep and more difficult. So, but basically those two names can be used synonymously. And neural networks are a computational model that is inspired by the workings of the brain, as you see in this picture illustrated down here. So the idea from a psychological and biological perspective is that the brain consists of something which what we see here in red, which biologists and psychologists and such kind of people call neurons, and those neurons are connected with each other they're connected to each other via those links, and then we have activation patterns in the brain. So if something is firing, it's also activating um, neurons with which it is connected. And then analogously, people in the 1940s, 1950s, they tried to come up with a computational model that mimics, or that is built upon those elementary conditions, namely having neurons, or we could also call them, if we are more in a graph-like terminology, we could also call them nodes, and those nodes are connected via some weights or links, right? And of course, having a brain-inspired model is something which, on first view, does not seem to be too bad an idea, because apparently our brain is one of the most powerful calculators that we can think of. It allows us to do all those fancy things like solving complex math problems, talking, recognizing objects. So if we ever want to be able to do this with a computer, then maybe let's use a model that builds upon the elementary units that a brain also consists of. So I want to start out with one of the simplest neural network models that you can think of, namely it consists of a couple of input units. You can also call them input nodes or input neurons. And they are connected to some other neuron, and we call this the output neuron. And what you see here, each of those units receives some input, which is a real number, and those real numbers, we denote them here by x1 to xn. And then You see here also connections between the input neurons and this what we call output neuron. So there are these connections here. So these are just links or weights, and they are also given by real numbers W1 to Wn. And then what's happening in this output neuron here is, well, it's taking a weighted sum of the input. So the input units, they have some activation, maybe from the outside world, right? Maybe we see an image of we see a cat. So the first units in our eyes or in our brain, they get some activation, or maybe it goes through the body into the brain. They get some sensory input, and then they are connected to some other unit, right? And now they induce an activation in this unit. And how do they do this? Well, first there's this linear sum. So we're summing up the inputs multiplied by the weights that we have here. And then we're considering this sum, and we're applying what we would call an activation function on top of this sum. And in the simplest case, this activation function is just a binary function. It's either 1 or 0. And it could be 1 if if this sum here, which we also call pre-activation, if this is, let's say, bigger than 0. If it's bigger than 0, then we say, okay, our unit here is getting activated. It also takes the output 1. If it's smaller than 0, then it's not activated. The output is 0. So basically, we see here that some new unit is being activated depending on the input, the sensory input, and the weights with which it is connected. Now in this example here, you see also here's a constant input with something where the weight is not called Wi, but it's called B. So this is what the neural network people call bias, but it's not so important now for understanding the concept, so I'll not talk about it. Okay, so we saw the elementary model, which just says, well, some unit gets activated depending on the, let's say, the sensory input that's coming in. We can, of course, not only have one unit, but we can have multiple units. So we have multiple other units that are dependent in our brain, right? So this is the metaphor. We have multiple units in our brain that get activated depending on the input and the connections between the input and those units. And if you want to do this if you take a mathematical perspective on all of those things, then what we saw here, this sum here is what mathematicians call a dot product. So it's like the input vector, so we have a vector x multiplied by this. So those weights, we can also accumulate them in a vector, we call them w. So you have x times w in the initial case, in this case here. And when we have multiple outputs, it's actually, it's what's happening is very similar, but you multiply the input x times a matrix to then get those pre-activations. And then on top of those pre-activations, you apply the activation function. And of course, we cannot only have we can have multiple layers of neurons that are connected. And they all depend on the input, right? So some inputs coming in that's activating the first layer of your neurons in your brain. And this then, this signal feeds forward to other layers in your brain. And they also get activated until finally you reach some output layer, so the last neurons in your brain, so to speak, and they also get some activation. So this is the mathematical model, the mathematical inspiration, and each of those layers is connected by a weight matrix, right? And if you have such a model, that would be called a multi-layer perceptron or feed-forward network. So again, perceptron is when you only have input and output, and multi-layer means you have multiple hidden layers here. Again, repeating the terminology that I have implicitly mentioned now, we would call each of those units here, we would call them either a neuron or a node. Maybe the term node is more popular nowadays because people forget a little bit about this brain metaphor and rather use more abstract mathematical terminology So people would call this node. And of course, there are multiple nodes here, right? And a node in the first layer, that's what we'd call input node. And the agglomeration of all the nodes in one layer, in one level. So all those nodes that are on the same level, so be it on the input or somewhere in between, these are called a layer. So we have an input layer, we have a hidden layer, another hidden layer, and then an output layer. And as I said, we have those what we call activation functions, which I denote here by sigma, tau, and psi. So these are also called nonlinearities, because what you've seen from a mathematical perspective, if you have a little bit math background, what we're doing is basically we're doing a linear operation. We're multiplying a vector times a matrix. So that's a linear operation. And then to make our model more complex and make it model more complicated things, we need to have some nonlinearity. So we add some nonlinearity there. So this makes our model a much more complex model, right? Because with linear models, you cannot model arbitrarily complex operations, but with nonlinearities, you actually can. And then this thing in the middle, that's what we would call a weight matrix. And oftentimes the individual nodes are not depicted. So if you read a paper, for example, they would only show you this layer-wise notation, right? So this is what you would typically see in a paper. And again, going a little bit into math. So if you like this brain-inspired picture that I've shown you, then you can go with the brain-inspired picture. But if you're more of a math guy, then you may like those equations that I show you now. And those equations are like summarizations of what I've already said. So I've said we have the input and we multiply this by a weight matrix. So what's coming out is this is a row vector times a matrix. What's coming out is another row vector. Then we add to this bias vector, which we ignore for the moment. Just ignore it. It's not so important. It's basically just making the model a little bit more powerful, but doesn't change the underlying mathematics. So basically what's coming out here is a vector, and then we apply a nonlinearity on top of this vector, and we apply this element-wise. So we have this is a vector of, let's say, n units. So we apply this nonlinearity to each element in this n vector, in this n vector. And what's coming out is, then again, that's a vector, and this is the hidden layer activation, right? So this is the activation what we have in the first layer. So this is basically the value that the neurons take in the first hidden layer. And then we do the second thing the same thing in the second layer. We take our first hidden layer activations, we multiply this by a matrix W, and again we get a vector. We apply our nonlinearity and we get another vector out. And this is then the activation in the second layer, and so on, right? So we can continue as long as we wish. Now, how do these activation functions look like? First of all, as I've said before, those nonlinearities are important because they make deep learning models powerful. How they look like, most of them map from real numbers to real numbers. So they take real number as input and they give a real number as output. And here are some typical candidates that you will see in the literature. And what you see here, for example, that many of them look like, if you look at those, well, they have some similarity. They have some similarity to this threshold function where I said either it's on or it's off. So either a unit, a node or a neuron, however you want to call it, it could be on and it could be off. And this activation function is is typically trying to modeling this, or the original motivation of those activation function was to model this, that the neuron is either on or off. But then if you only have a binary function, then you have problems of optimization, you cannot differentiate, etc. So people try to find an approximation to this on-off function, and here you see some approximations, right? And then over time, those changed a little bit, and they look like this. Nowadays, and there are even many others around. We're not going into them, but I just gave you some intuition of why they would have those shapes that are sketched here. And there is a particular activation function which I call softmax, or which we call softmax. It does not work on, it does not operate on a single neuron, but it operates on a whole layer. It acts on a whole layer. And what it's doing is it makes the activation a probability distribution. So what's a probability distribution? Probability distribution in a discrete space is it's just something that's assigning each object a number between 0 and 1, and the sum of those numbers have to add up to 1. So you can say object number 1 has probability 25%, object number 2 has 30%, and object number 3 has 45%. So I hope that this adds up to 1. So that's a probability distribution. And in neural network terms, we have a layer. So a softmax acts on a whole layer. So there are, let's say, m nodes in one layer. So it just makes a probability distribution over those m nodes. So it would say node number 1 has probability 10%. Node number 2, actually the output of node number 1 has probability 10%, etc. And what we can use it for, we can use it for classification. So we would apply it to the output layer, and let's say we have like m objects that we want to categorize, or we want to classify something into m different classes. Like class 1 could be politics, class 2 could be sports, and class 3 could be science. So if we want to classify a newspaper text in terms of its content, so we could have those 3 classes. And then we would want to assign how likely it is that our given input, like our given newspaper text, is about politics, is about sports, is about science. And so we would want to have a probability distribution, which would say with 80% it's about politics, with 10% it's about science, and with 10% it's about sports. So that's why people oftentimes, when they do classification, they use this softmax activation function in the output layer. And from a high level, neural networks, if you want to look at them from a mathematical perspective, they are those mathematical functions. And here I make an abbreviation. I take a two hidden layer neural network. And this network takes an input x, which is like the sensory input that's coming inside. If you want to look at it from the perspective of the brain-inspired metaphor. So some inputs coming in, and then we have those two weight matrices W and V for a two-layer neural network. And what we do is we apply the first. So we multiply x times W. We then apply a nonlinearity f, or sigma tau, however you want to call this, and we get an output in the first layer. We multiply this and then apply the second activation function g. So it's basically a composite mathematical function that's doing those linear operations, x times w, and then applying nonlinearities on top of them. And then if we want to train a neural network, and this slide here is maybe a little bit too complicated for you if you don't have a math background, but I just give it to those people that have some understanding of math. What we then do is we define a loss function. So we say we have a data set, and this is very typical for machine learning. We always have a data set which gives us instances and examples of what we should learn. For example, each instance could be a picture and a label, or each instance could be a sentence and its label. So we say this picture is a cat, or this sentence is actually, or this newspaper document is actually about politics. So these are our examples. And then what we do is we feed our examples into our neural network. It's making some output, it's making some prediction, and we compare it to the actual true label that we have. So we would say this document is a cat, is about politics, and now let's see what our network is actually outputting. So if our network says, no, that's about sports, then our network does not make a good prediction. So what we want is that our neural network makes an output prediction which is close to the actual label, and we achieve this by taking this norm here. So this is norm, and then we square it, and the further our network is from the true label, the more it gets penalized and the more its loss is. So this is what we call a loss. And the higher the loss, the worse, right? We want low loss. Ideally, we want zero loss, right? And those theta here, that's what machine learning people call the parameters. And in neural network terms, these are just W and V in our two-layer neural network from above. And now what we want to do is we want to optimize our parameters theta, our weight matrices, such that our loss becomes minimized. And this is what we call learning or training. And so basically we have a loss function that's given by this form here. I want to optimize, like we want to minimize our loss. We want to set our parameters W and V such that our network makes very good predictions. And when our network is capable of doing so, then we know that it's classifying a good fraction, or ideally maybe all instances in our training data correctly, because if the loss is zero, we would like make a correct prediction for each input in our training set. And then we hope that this actually would generalize to some unseen test data. And how do we optimize our parameters theta? Well, that's a numerical optimization problem, and which I cannot go into now in this small high-level overview of neural networks, but actually it's solved with something called backpropagation. Now, as I've already indicated, deep neural networks are an instance of machine learning, and machine learning could be characterized as the field that is trying to learn patterns from data. So we have data, and these data examples. I want to learn somehow how to map, let's say, the input to the output, right? So we want to, that's also what humans learn, right? When you're a baby, you need to learn that something is a book and something is a cat, right? You learn this also from examples. Somebody's showing you, usually your parents are showing you, these are examples of a cat, that's an example of a book, and then you are adapting yourself, your parameters in your brain, so to speak, and you learn to label those things correctly. And when we're in the field of machine learning, then let's go into some terminology. So there are different types of machine learning. So there's supervised learning, unsupervised, self-supervised, semi-supervised. I just go into the first two. The others are like variants of or mixtures of those first two. Supervised learning is when you have label, right? This is like your parents telling you, that's a cat, that's a book, and that's a baby. And the unsupervised is you don't have any labels. You just get some instances. But nobody's actually telling you the labels that those instances have. And you need to figure out yourself how to classify, what to do with this data, right? And then semi-supervised, for example, is just a mixture. You have a little bit of labeled data, and you have much less unlabeled data, much more unlabeled data. The second concept is train-def test splits. So usually we have a train split, and this is this, for example, in the supervised setup is what we train on. This is our samples, our examples of like cat, dog, and book. Then the second part of our data is what we call the test split. So this is where we evaluate the performance of our model. So first we train our model on the train set, but then we need to assess the quality of the model on some other data set. So because we want to see how well can our model generalize. So if we go back to the baby, so first we show it a small cat, and then afterwards, of course, we hope that at least the baby can memorize if it's smart enough. So it can, again, if it sees the small cat, it can say that's a cat. But then afterwards we show you the big cat, and that's a real test case, right? Because that's what is never seen, and we hope that it will recognize that this is still a cat, even though it's like bigger or something, or the color of the hair is different. And then this def set, so we also have a def set, which also goes by the name of development set. That's where we do some tuning. So in machine learning, we have usually something which is called hyperparameters, which doesn't depend on the model, but is like something external to the model, like it could be a part of the optimization algorithm, and there we tune those hyperparameters, right? We find the ideal combination, the ideal values, so to speak, of those parameters, and then we apply them later on the test. There's also something called cross-validation. Let's assume you have a data set of 1,000 instances X with 1,000 labels Y, and then we could train like on 900 and test on 100. So we can do this once, but well, and then we get some. We can assess the quality of our baby. How good is our baby in labeling new books and new cats and new dogs? But we would only use 100 as test data. So we can also, 100 may be a small size, right? So the estimate of the quality of the baby of the machine learning classifier may be inaccurate. So we can do it again. We take another 100, another 900, so different 900 ones, and test on the remaining 100. So we get 2 instances where we can check the quality of the baby of the machine learning classifier. Then we take the average. So that's going to be a little bit more precise, because then we have actually tested on 200. And we can do this n times, right? And then take the average, and we're getting more statistically powerful estimates of our performance. And then another terminology in machine learning is the evaluation measure. How do we evaluate our model? And there are different ones like accuracy, F1, BLEU, recall, depending on what you're actually doing. Accuracy is often, if you have a classification context like the one I've just sketched, we want to classify objects into categories or text into categories. F1 is when you have an imbalanced data set. Let's assume most instances are of class 1 and only few are of class 0. So let's say a very rare disease, right? So most people just don't have it, so they're all zeros, and just a few people have it, so they are ones. And then it's very easy to get a high accuracy. If you just predict that nobody has it, then you get a high accuracy. But in this case, you would use a different performance measure, which is called F1. And then there are BLEU. BLEU is something, if you do machine translation, you cannot just get the accuracy, because probably there are infinite number of strings and infinite number of ways of producing an output text. So if you use accuracy or F1, you will almost always, your system will not reproduce exactly what the desired output is, but it can be close to this. It can be different, so it can be a different text, but still this different text captures the essentials of the other text, so it could be equivalently good, and that's what we call a paraphrase. And there we need then another measure which can and such measure in machine translation is called BLEU, and there are other ones. Then there's also something called overfitting, and this is when you match. The your training data too much, right? If you just match exactly your training data, then most likely you're not gonna end up with a good model, because matching the training data is actually very easy, right? You can just you can always find a function that exactly matches your training data. So by just like assigning a function that's looking if something is in the training data, and if it's in the training data, just give it a label that's in the training data. But then such a function, such a model, that would perform very badly on it would have no idea how to deal with unseen test cases, because they're not in the training data. So if a big cat comes in, it's not in the training data, has no idea how to label this. So this is like, this model would completely memorize the training data, but have no clue what's going on in the test data. So that would obviously not be a smart, that would not be a smart baby. So we don't want, actually we don't care so much about the training data accuracy, but we care about the accuracy on new test data. And if a model is just very good in the training data, but not good in test data, that's what's called overfitting. And then finally, there are different techniques of machine learning. So one of them is a neural network, what we just introduced. So this is one particular model class. So it uses this class of linear operations together with nonlinear functions. But then there are also other model classes that use other mathematical formalisms, and those go by the names, for example, of decision tree, support vector machine, k-nearest neighbors. I'm just throwing in names now so that you have heard about these, but I will not go into details now. Let us briefly look into the history of neural networks. So in the history of neural networks, as I've indicated before, everything started out in the 1940s, 1950s of the last century, where people came up with this perceptron algorithm and this perceptron model, which I introduced before, where we just had inputs, and then those inputs were connected to some other neural network, to some other neuron, to some other node, which would also call output neuron, and there were no hidden layers. So that's what would be called the perceptron. Then about a few years later, people like criticized this perceptron. They found out it is actually cannot do very much. So there's this famous case of the XOR function. So if you're a computer scientist, you know what the XOR function is. You also know what the OR and the AND function is. So the AND function is, it takes two arguments, both are binary, 0 or 1. And then it says 1 if both of them are 1, and if one of them is 0, it says 0 as output. And the OR function, it says, it gives as output 0 when both of the input arguments are 0, and otherwise it gives an output of 1. And the XOR function is like, it gives an output of 0 when the arguments are identical, and it gives an output of 1 when the arguments are different. So 0, 1 is mapped to 1, 1, 0 is mapped to 1, 0, 0 is mapped to 0, and 1, 1 is mapped to 0. So this is like, that's the XOR function. And people found out that this perceptron cannot even learn this XOR function. So this is a very basic function that is not able to learn it, right? So how good can this perceptron be if it cannot even solve such a simple problem? But then later people found out, okay, if we have those hidden layers, they give really much more power. Then those hidden layers, they can learn more things. And actually what's been found like in the 90s, so this is not here, what's been found in the 90s is that if you have multiple hidden layers, you can actually approximate all possible continuous functions. So actually with a neural network you can really like model most things which are relevant from a practical application perspective. So actually neural networks are powerful. But then for a long time people didn't know how do we find these optimal parameters for our neural networks? How do we actually learn, right? So that has also been a problem, and then was solved like in the 70s and 80s with the backpropagation algorithm. And then mostly in the 90s, neural networks were not very fancy. Most people didn't use them, so other techniques like support vector machines were cool. There were individual successes, for example, Jan LeCun, which you see pictured here, where he developed a system that could like digitized handwritten. So if you were writing a mail letter with those handwritten, so it could automatically digitize this. Also, Geoffrey Hinton and a few other people, they were like still working on this, even though the most part of the research community didn't use it anymore. And then everything like taking off around the start of the 2010s, when there was this something called AlexNet. So this was a model in the computer vision community that could actually could perform quite decently or quite well on image classification. And also Google Brain had some projects. And this is also the time when in natural language processing, Tomasz Mikolov came up with word embedding. So these were all neural network architectures. And then it really kicked off, right? People started to finally see that those things are powerful if we have the right, if we have enough computing power, and if we have the right mathematical approach and the right optimization approaches. So it took a long time for those neural networks to kick off, but finally, it seems like starting from around the 2010s, we finally learned how to use them properly, and now they are like, they had huge successes, and some of those successes can be shown here. Like this is image classification. We have here the error rate, and we see the best model on this image net is like image classification. So you have an image, you shall label the what you see in the image, right? And then 2010s we had like an error rate of slightly below 30%. So 30% of the images were falsely classified with the best system at the time. This was not a neural network. This was like a traditional computer vision approach. And 2011, the error rate goes down by a little bit. But then in 2012, we see like neural networks coming in, and they very quickly, they go on the level of humans, right? So this is like a big success. If we go to my community, natural language processing, we can also see something like, especially if you use like Google Translate, let's take a popular example. In 2010s, you would notice that it's not performing very well. If you use it nowadays, you see that it performs actually very well. And here are some use cases. Let's say we want to translate from English to Spanish, English to French, English to Chinese, Spanish to English, French to English, or Chinese to English. So there are different things. Then we can check how well does a human perform, like a native, a bilingual speaker, right? For example, how well does he perform? We can like somehow assess the quality of the human speaker, and of course most human speakers are not perfect, so it's a little bit away from perfection. And then we have also this phrase-based machine translation. So that's the old approach that was dominating from the 1990s to the 2010s, and you see it's coming close to the human bilingual speaker, but it's still also quite far away. And then on the other hand, we see the neural network based approaches, and they had much less time, right? Just in a few years, while the others had like they had like 20 years, right? And those had just 4, 5, 6 years, and they actually came much closer to the human upper bound, so to speak. Good. So here's a graphic which is not of high quality, but also illustrates some use case of neural networks. And this use case illustrates when neural networks typically perform well, and this depends on the size of the data. So if you have very little data, then you better go off with traditional machine learning. Traditional machine learning, this could be like defining rules by hand, or it could be using linear functions, or it could be using something called features. So where you define features. A feature could be, is the first word in this text, let's say, is that neural, right? So this could be the first word in the text, and then if the first word is neural, then maybe it's about machine learning or something. It's about deep learning. So that's a handcrafted feature. So these are traditional approaches. And when you have very little data, then typically they perform better. And the more data you have, the deeper can your network be, right? If you have very much data, then you can make many hidden layers in your neural network, and then you will get much better performance than if you use just few hidden layers or very few hidden layers, or if you use traditional machine learning. And why is this the case? Well, obviously you can imagine such a deep neural network with very many layers that will easily overfit. So that's a very powerful model, right? It can like approximate every function. But now if your training data is very little, it will find a solution that is completely overfitting your small training data, because there are many solutions for such small training data that can explain, like if you only have 10 training data cases. So there are many possibilities to explain this, and your network will find a way to exactly explain the training data. But this often is also not good to exactly explain the training data, because the training data may also contain noise, right? Something may be mislabeled. The human was not sure, the human was sleeping or something. It made a label change or a measurement error. So if you fit all this noise, so this is noise in the training data, and if you fit this noise, then you're probably not going to perform very well on test data. So with very little data and you throw in a very powerful model, you're typically not gonna end up very well. But if you have very much data, you probably also need a complex function to model this high amount of data, and that's where deep networks kick in with their performance. So what does not work well nowadays with deep networks? So one thing that I've already shown is like small data scenarios. Another thing is transfer, generalization, robustness. So that is when usually many machine learning and deep learning approaches, they work under a so-called IID assumption. That IID assumption is like the distribution of the training data is the same as the distribution of the test data. So basically, you're gonna train a classifier on newspaper corpora, and it classifies every document into politics, sports, or science, and then you assume that your test data is also a newspaper corpus. But what if your test corpus is social media, such as Twitter or Facebook? And then typically those models perform badly, right? And this is because the models often lack deep understanding. So they exploit low-level statistical cues. So this is like they find some solution that are like not in the way that humans understand data. So for example, the solution could be, well, if something starts out with if there's a score like if there's a three-letter digit such as 1:0, then it's likely gonna be about soccer, right? So this is a low-level statistical cue that such a model could learn, right? That because if there's 1:0, that's likely a soccer result, right? So they could say, okay, that's about sports. But that's not usually how humans would treat this, right? We would not only go for this one cue. We would like read a newspaper text and then find a generalized representation. And even in a document about politics, it can happen that there's such a soccer score, right, embedded somewhere in the text. And then those models, those neural networks and other machine learning models, they usually lack such kind of deep understanding, and that's why they fail. There's also a classical example. Let's say you have an image classifier which correctly predicts that this is a pig, and then you can add some noise, and this is not random noise, this is some carefully crafted noise, you add this and out comes this thing here, which to us looks totally identical, right? So we would still label this as a pig, but our neural network picking up on some low-level statistical cues, for example, would make a completely wrong output prediction. So these are challenges for neural networks. To some degree, they are being tackled at the moment, and there are also already some solutions. For example, in the natural language processing community, we have this BERT model, which allows for better transfer between domains because it has been trained on huge amounts of data. So basically, it has seen all domains because it has been trained on the whole of the web, so to speak. So it has seen many domains, and then therefore it can also generalize easier to different domains.